Hi guys, in this video let's look at the Intro to Alkenes handout. Now this handout begins with Nomenclature of Alkenes, and that's actually covered in a separate video. So I'm not going to do that here. In that video I cover the first page, the second page, and then also I take a look at the back, which is an article about refrigerants. And it shows a couple of common refrigerants, and you'll see that these are each alkenes with these halogens, with fluorinated alkenes being some common refrigerants. But these include the IUPAC name for each of these alkenes, and so you can use this to test your knowledge of nomenclature. Don't look at the name, name these, then look back at the name for the answer. There's also just interesting application of some alkenes. But in this video I will name this alkene as practice. So you can pause the video and try to name this alkene. Now if you haven't looked at the alkene nomenclature video yet, watch that. Maybe you can see me go through the naming of this compound here. Then you maybe can go back and look at the alkene nomenclature and be better prepared to understand that perhaps. Okay, in any event, let's name this alkene here. It's an interesting molecule, got a couple of halogens, lots of hydrocarbon, but it isn't, the main functional group is an alkene, so we're going to name it as an alkene. Longest continuous chain that contains both carbons of the alkene would be 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. 7 would be longest. So it's going to be not a heptane, but a heptene. And we need to indicate where the alkene is located. It gets priority for numbering, so let's do that first. It's either at the 1, 2, 3 position, or it's at the 1, 2, 3, 4 position. Well, 3 is better, so it is a 3 heptene. It's at the 3, 4 position. We only list the 3. Okay. What is on the 3 heptene? Well, we have a chloro. We have this group. It's an isopropyl, or we can name it by IUPAC as a complex substituent, and we have a bromo. Those two are straightforward. By the way, that's 4, 5, and 6. And so this would be a 1, 2, call that maybe prime. What is that, a 1-methyl ethyl? Alphabetical. B comes before C. What do we have here? 6 bromo. Three chloro. 4 dash, what's at the 4 position? A 1-methyl ethyl dash 3 heptene. Okay, seems good. If we were allowed to use common names and we wanted to do that, instead of 1-methyl ethyl, we could have said 4-dimethyl dash isopropyl dash 3-heptene. And B, C, I would still have been alphabetical order. Now, this alkene is stereogenic. Okay? I can tell that because this alkene can be either E or Z. Okay? E or Z possible. We thus need a stereochemical descriptor in front of this name. We can do that. Again, that was described over in the other video. Okay, on the second page. On this carbon of the alkene, what's high priority, chlorine or carbon? Well, chlorine. On carbon 4, the other carbon of the alkene, what's high priority, carbon or carbon? Well, it's the same thing. So we need to look at what's on each of these carbons. What's on carbon 5? Or this carbon? Carbon, HH. We list those, okay, with the highest priority first. Carbon, HH. What's on this other carbon? Carbon, carbon, and H. Carbon, carbon, and H. We list these in high priority. If we got 2, we just list them both. Okay, now we look for a winner. Which wins, carbon or carbon? If there's no winner, go to the next. Which wins, carbon or H? Carbon wins, and so this group here is the highest priority group. That's this group here. And so we identified the 2 higher priority groups, and they are cis. And when the high priority groups are cis, it would be Z. The same side. The groups are on the same side. They're cis. So that's our stereochemical descriptor. It goes in front here, in parentheses, dash. Because, all right, stereochem descriptor. If we start using a stereochemical descriptor, that means that the compound has stereochemistry and stereoisomers are possible. What would the stereoisomer be? It would be the other isomer, other stereoisomer. It would be E. And then, of course, same exact name. Because stereoisomers have the same exact name, they only differ by some type of stereochemical descriptor. They have the same name because they have the same exact connectivity. On the other hand, constitutional isomers have different names because they have different connectivity. What would the E stereoisomer look like? Well, it would be, the alkene would be there. Put the chlorine here and the ethyl group here. We would switch these 2 groups, and the isopropyl would be trans to the chlorine, not cis, and in the other group, which is a carbon, carbon, and then a carbon and a bromine, okay, this has the same exact name. The only difference is the stereochemical configuration around the alkene. It's still 3-chloro, it's still 6-bromo, it's still everything. It's just now E, where this one here was Z. All right. Now note when we determine E and Z up here, we look at first atoms as we move away from the alkene, carbon or carbon. Then we look at what's on those carbons. Doesn't matter that the bromine is out here. We never made it out that far. Okay? All right, so you can look back at that. I think we covered everything. So there's an example of nomenclature. Let's now look at next page here. Physical properties of alkenes. A couple of miscellaneous things here, but then also a very important thing down here at the bottom. Okay, question. Now, just to orient you here, there's a couple of questions here on this page. Of these two, which has the highest boiling point and which is most stable? And which is most soluble in water? For these two, I ask which is most stable. For these four, I ask which is most stable and which has the lowest heat of formation. And which of these four gives off the most heat when burned? So you might pause the video at this point and try to think about some of those before we move ahead. Okay, which of these two, well, what's the difference in these two? These are just stereoisomers. They both have the same name. The difference is this one is trans and that one is cis. Or you can call this one E and that one Z. So they're just stereoisomers. So which of these stereoisomers will have the highest boiling point? Well, how have we judged boiling point before? It's mainly due to IMFs, and we can look at these and ask which one is more polar. They all really have the same IMFs, but the key difference here is polarity. If we look at dipole here, those two there versus this compound is non-polar because the two individual dipoles are equal and opposite, but this compound, they're equal but they're not opposite. They actually reinforce and you get a single molecular dipole moment that looks like this, and so this is a polar compound with a partial plus side and a partial negative side. These partial plus and partial negative sides are going to start sticking together as IMFs, intermolecular forces, or intermolecular non-covalent interactions. That's going to lead to stickiness, and that's going to lead to a higher boiling point for the polar one. Which one will be most soluble in water? Well, again, we're looking for the most polar. We found the most polar. The more polar one will be more soluble in the polar solvent, because the polar solvent itself has partial plus and partial minus areas, and those can interact with the partial plus, partial minus areas of the polar molecule. Certainly much better interaction. Okay, which of these two will be most stable? Well, here let's remember what we did with conformations. By the way, these two are not conformations. Okay? These are stereoisomers. E and Z stereoisomers are cis and trans. These do not have free rotation. Okay? We had two groups here. This pi bond cannot rotate. All right? We cannot turn this one over. The two groups would be opposite. They're stuck there. All right? But if we think back about conformations, we talked about how the largest groups want to be anti. And that's the same here. And in this molecule here, the chlorines are anti to each other. Trans or anti. And that's the most stable sort of arrangement here, and it's thus the most stable compound. Largely a steric factor or a steric argument. Okay, below, which is most stable? Well, down below, what's the difference? This alkene, 1, 2, 3, 4, 1, 2, 3, 4, is disubstituted. And this one is monosubstituted. That if you just look at the alkene, carbon-carbon alkene, this carbon has one substituent, a methyl, this carbon has one substituent, a methyl, and so altogether that's two substituents on the alkene disubstituted. If you look at this one, there's only one substituent, and that is the ethyl group. The other atom here, bond here, is to an H, H, and H, and we don't consider H's as substituents. So that's the main difference. And these two are not stereoisomers, but these two are constitutional isomers, right? Now, the way to answer this, let's actually look below at this table down here. And this shows 4 different alkenes, and they're all constitutional isomers. And they're ranked in terms of stability. And you see that the first one is a tetrasubstituted alkene. It's the most stable. The next one is a trisubstituted alkene, then a disubstituted alkene, and then a monosubstituted alkene. The more substituted alkene is the most stable. The least substituted is the least stable. Now that should be pretty straightforward to know. But why? Why is that the case? It all has to do with the types of carbon-carbon bonds that are in these molecules. Now, each of these alkenes has a sp2-sp2 sigma bond. That's the sigma bond in the double bond. So they all have one of those. The difference is here. All right. So let's not really consider that. Let's consider these two. Of these two, which is stronger? sp2, sp3 or sp3, sp3? . Well, the first one is stronger. And the more substituted alkene has more of these stronger bonds. I will highlight the stronger bonds, sp2, sp3. That there, that there, that there, and that there, you may or may not want to write on your paper here. But those four are all sp2, sp3 sigma bonds. This one only has 3 of those. This one only has 2 of those, and this one only has 1 of those. You see, instead, this one has more of the sp3, sp3. Has 3 of them. Well, actually, the first one has no sp3, sp3 carbon-carbon bonds. In the end, the more substituted alkene is going to have more of the stronger bonds, and thus it's going to be more stable. Now, importantly, we're typically talking about carbon substituents. If the substituents are to other atoms, sometimes this can change a bit, but usually when you see this type of question, you're asked to consider mainly carbon substituents. Okay. Very important concept. We will refer to this many times, and typically you guys will forget this. Okay? Don't forget this. Very important. So let's go back up here. Which one of these two is most stable? Okay. Well, it's the disubstituted. That's it. Should be pretty easy. We explained the reason down here. This one has 2 of the stronger type carbon-carbon bonds. That one only has 1. The other carbon-carbon bond is a weaker type. Let's try again. Of these 4, which is the most stable? Well, actually, those are the 4 that are down here if you look at them. And the most stable is this one here. But next question, which one has the lowest heat of formation? Do you remember heat of formation from Gen Chem? Lowest heat of formation would be... Have we seen heat of formation before? I think we did, didn't we? During test 1 material, heats of formation. Which rings were better? 5 and 6. These had a lower heat of formation compared to the more energetic or less stable rings. Okay. The lowest heat of formation is going to be the same one. The question is really which is most stable. Hopefully you understand how to think about a heat of formation and such a question. Okay, third question here. Which of these 4 gives off the most heat when burned? Maybe you want to burn these as a fuel, maybe to light your grill and cook your hamburgers or your grilled chicken or something. If all of these cost the same amount per liter of of the gas or for a container of the gas, which one would you want to buy? The one with the most heat, the one that gives off the most heat, or the least heat? I would want the one with the most heat. The one that gives off the most heat is going to be the first one. All right? That would be the one that is least stable. Because least stable usually equals highest potential energy. Okay. There's a question over here to the side. These are 3 natural products found in some plants and spices, such as nutmeg. These are constitutional isomers. The alkene is connected at different positions. Rank these in order of stability from most stable to least. Typically, when you're looking at sort of alkenes, we're looking at this here. The most substituted alkene is going to be the most stable. And the most substituted is tri-substituted, di-substituted. Oh, hold on. Both of these are di-substituted. Yeah, but to rank these in order of stability from most stable. This would be most stable. Right, it's tri-substituted. Both of these are di-substituted. Well, we don't have enough information. Nothing that we talked about distinguished between these two. They're both di-substituted. Here the substituents are on different carbons. There are cis, but they're on different carbons. Here the substituents are on the same carbon. Okay. So I don't think we have enough info to distinguish between these two, but this one is certainly the most stable. Here. Okay. Next page. These are some fatty acids. Now this is a little bit of an application, but there's important information here. You may have heard about some fatty acids are not too healthy. But actually some are more healthy than others. The first one is stearic acid. It is a saturated fatty acid. And when we say saturated, that refers to the side chain. Now it does have a degree of unsaturation here. But the side chain is saturated. And saturated fats tend to be bad for you, and that's because they tend to be solids at room temperature. And even at body temperature, and so they're more likely to form solids in like your arteries or veins and cause problems, clogging up your arteries. But if the side chain has an alkene in it, particularly a cis alkene, look what it does to the melting point. It lowers it significantly. And so these are liquids at room temperature. So they're not going to form solids in your arteries as likely. and so they're not going to cause as much health risk of clogging your arteries. Now the Cis Alkene puts a kink in the chain. See, this can be very, very straight, and because it's very straight, the different molecules can start just sort of all coming together real close. Okay, I don't have 4 identical pins, but they can all just come together and stack on each other and get real good van der Waals attraction between each molecule. But if you put an alkene in there, all right, I mean, these are coming together, you know, like this. If you put an alkene, it's going to have a kink in it. And I don't know if I have anything with a kink in it, but if it had a kink in it and it tried to line up, okay, it's not going to sort of come together as well because of that kink. So it's not as straight. So that's what that alkene does, and that's particularly the case when it's cis. Now this would also be called a mono unsaturated fat. Those are typically the more healthy type of fats. You can also have a polyunsaturated. Okay. These are also considered more healthy, but these are cis. Both of these are cis. And then you can have one here. Now down below it has a cis alkene, but it also has 2 trans alkenes. And you might think, well, the cis alkene, just like this one up here, can cause kinking in the chain. Yes, it does. But the trans alkenes actually increase the melting point because the alkenes are polarizable. Alkenes tend to be polarizable, and when we put trans alkenes in there, it raises the boiling point or melting point in this case, and now we're back up to solid. And so the solid ones are either fully saturated or they have the trans, okay, a trans fat, and you may have heard that term. A trans fat is typically bad for you. So this is just a little application of how the cis or trans double bonds can affect the physical properties of fatty acids. Now, just a little bit more information here, because it's general stuff, but it's pretty sort of important to understand the chemistry that's going on here. These cis unsaturated fats tend to be more natural, like in olive oil. Some good oils. Problem is, your alkenes, they're not always that stable. They can be air oxidized, and so the oils don't last long. And so that's why what you can do is you can saturate the side chain and make saturated fats, and these will last longer, and you can cook with them longer and reuse them. But unfortunately, they're not as healthy because they'll solidify in your arteries. Now, I can also note that the trans fats, these are not always that natural. What happens is, sometimes when you remove the double bond, we can get saturated fats, but sometimes the double bond will actually become trans in that process. So kind of a side product. In the end, it's best to use natural fats that have more of these cis double bonds, either one monounsaturated or multiple polyunsaturated. Okay, the remainder of this handout is a couple of drug applications and identify each stereoisomer below as E or Z. These are stereoisomers. Both are given when you take this drug. It's a drug for insomnia. The one on the other side is very similar, but it has this carboxylic acid side chain. It's an antihistamine drug, but you can also determine if it's E or Z for practice. Okay, so this is some miscellaneous material here, guys. Nomenclature. But we also looked at the important concept of stability of different substituted alkenes.